Good morning, everyone. First, let me check. Prof, is that you in the contact list?
Hi, Molebo. Hi, everyone. I'm here.
Perfect. Perfect, perfect. Thank you so much, Prof, for joining us. I know it's quite early in your part of the world, right? Uh, so welcome to yet another session of the BRICS Data Analytics training course. So this is probably the last 2 weeks of that the course will run. And for this session, we have the privilege of having Professor Reynaldo Rosa from the National Institute of Space Research in Brazil, and he'll be touching on explainable AI. And I hope you enjoy the session. Prof, over to you.
Thank you, Molebo. Thank you, everyone, to be here. It's a pleasure to be here again to talk to you about XAI, Explainable Artificial Intelligence. So, give me just 30 seconds so we can start. I just open I'll share my screen. Just a minute. Okay, let me know if everybody is seeing my screen. I have,
Yes, we can see your screen, Prof.
yeah, okay. So we are going to module two. Okay, weeks ago we have the time series analysis as the mod.
Hello?
Hello, hello. Can you hear me?
Yes, we can hear you, Prof. I think someone's mic was just unmuted for now.
Okay. So we are going today to the module two, where we are going to discuss the concept of artificial intelligence in a new framework that's a very important one that we call XAI, Explainable Artificial Intelligence. Of course, everything we are talking about in this course should be very important to you in terms of new concepts, maybe. Uh, and we can apply all those concepts for any areas, not only for physics and astronomy, of course. That's a very important one. And today I'm trying to explore the concept on a few applications in space weather forecasting. In the afternoon, we will see XAR for astronomy and astrophysics with also concepts and some hands-on, taking the help of Mariana Rubet, that's a postdoc research in our institute. She is from National Observatory in Brazil, also in Brazil, and he has a very high level of expertise in those tools. Okay. I think the best way to see XAI is like to trying to see the concept in a very broad perspective. Okay, so so that's the first step in this today's course. So then we will show just two tools from XAI that is very famous nowadays. One of them is the SHEP, and the other one is Lime. This is important because you can bring to you as a course a little bit of the mathematics inside this black box. Actually, XAI, that's the main goal to bring XAI to you, is trying to open the black box that is, let's say, behind all the applications that you are familiar in using artificial intelligence methods, especially machine learning and deep learning models. Then we will discuss XAI in a very real application. That's for Embrace. Embrace is the Brazilian monitoring service for space weather. Okay? In Portuguese, it means Estudo e Monitoramento Brasileiro do Clima Espacial. Okay? The Brazilian Student Monitoring for Space Weather. This is also a lab, a very important lab in South America. There is one, the same one in China, okay, and also there is one in USA. For BRICS cooperation, we have let's say a very good team from China in Brazil working on this lab. So we will explore. We are going to explore two models. Model one is trying to predict the ionosphere activity from the auroral jet that we call AE time series. We are coming back to time series now, but in a XAI framework. So all the activity we see in this model comes from solar activity, starting from GOES, that's a satellite that can get the X-ray irradiance from the sun. And of course, it goes to do some effects, to make some effects in the magnetosphere. And there is this time series that the measure of the perturbations in our geomagnetic field. We call SIN-H, this time series. And then we have here this kind of cause effect pipeline since from the sun activity to ionosphere. But we have also a model 2 that's not only for time series, but is for images, okay, that came from this Solar Dynamic Observatory. That's a spacecraft in the nearby around the Earth. And this Solar Dynamic Observatory can give us one step back before what we see in the time series. So model 2 is still very, very important because we can start from model 2 and goes to model 1. Okay, that's a very hard thing to do, but is the future of space weather predictions. And then we're going to conclude the remarks where I'm going to show you very, very amazing ongoing research and development with some innovation for space weather applications, especially space weather services. So that's very important. That's an open door for all young people that want to work in space physics. Okay. Okay, let's go. So that's the time series that we explored in the first module of our data analytics course. This is for the sunspot number. Okay, we have this cycle that everyone that were in the first part of the course saw. We see here the measurements of the sunspot number along many years. So we choose 3 cycles just to show you where we are now. We are trying to predict using artificial intelligence here. So we have this panel prediction that we call. There is some moving average here, okay? In violet here, the smoothed monthly values, and you have the real monthly values measuring. And of course, all those dynamics is related to this image where we can count the sunspots on the solar photosphere. Okay, so as we have AI here, please pay attention what I'm going to say. You know, we are doing some predictions for solar activity, and we know solar activity as a very, very important issue concerning many dynamics around the Earth, especially for space missions, also for our power plant, also for our climate. So we have influences of the magnetized atmosphere around the Earth to the climate. So there are many critical things that we should be able to understand, and we should be able to explain. We should be able to interpret. We should be able to audit, and we should be able to also do accountability, because if you get some wrong results from AI here, we need to understand very well what's going, what's happened, what is inside the black box of AI, because it's a critical area. The same way we have other critical areas, maybe much more critical than climate. That is, for example, health. When you are doing with health in hospitals, for example, if I use some kind of prediction for about human diseases or human conditions, it is also important for astronauts in space. This is much more critical because any make decision at the end of the end-to-end pipeline, okay, based on some AI application, it will be could be very, very dangerous if you got a mistake based on AI. So that's the first discussion about the importance of explicability, interpretability, auditability, and accountability related to AI applications. And for space weather, as I told you, the first model takes data from the GOES satellite. This satellite is giving us this kind of time series. That's time series where we have X-ray flux here in this range of watts by square meters in this frequency, 0.8 nanometers for X-ray flux. And with this 1 minute resolution, each minute we have one measurement of this X-ray activity from the sun. This is a very important data because you can classify from the peak of this X-ray emission which kind of flare is coming from the sun. We have the B class, C class, M class, and X class. X class means the most powerful flares, like this one. And here on the right, you have another example where we have at least three or four X-ray X-class flare. One here, two here, one here, and another one here. Okay, and we can see from those data below the GOES, okay, the influence in our planet. Here we have the CNH time series in nanotesla. This is signature of anomalies in our magnetic field shield around the Earth. So you see in this, there is a delay, of course, about 6 hours from what happened here and what happened in our geomagnetic atmosphere. So we see, okay, some decreasing values or some modifications in our geomagnetic configuration due to those flares, the very big ones. So at least two of them. And here we have the auroral electro jet, where we can see also some very, very modifications in the electrical content that is coming from the sun to our polar ring around the Earth. So that's a kind of a very, very, very clear influence from the sun to our planet, and we can get that from time series. Okay. Please, if you have any questions, you can ask me, and otherwise you can go ahead. Okay, so when we are talking about applications of XAI using some techniques, for example, we will see in the afternoon module the long short-term memory technique, okay, for solar activity prediction. What is long short-term memory? Is a kind of a recurrent neural network that we can use the configuration I'm going to show you in at the final of this talk, during this talk. The long short-term memory is a AI architecture where we can see some gates that we call uh, um, uh, remembering gates and the forgetting gates, where we can mimic some kind of memory in these kind of neural networks. But that's okay. That's not the it doesn't matter. Could be anyone here that we are using for solar activity prediction. Okay. So when you say XAI, we are talking about two orders of XAI to explain prediction. Okay. The first order, we are trying to use XAI to explain the models. And the second order, XAI, explain the modeling process and its performance. If it's based on the results, because if you apply AI, you say, "Oh, that's a very good result." That's okay. I'm pretty sure that's a very good result. Why? Okay, why that's a very good result? Because it works. It was a prediction, and then from that prediction, I got some effect, and I measured those effects. So it means that AI works very well. So I'm very happy. But when the results are wrong, are not good performance results, what I'm going to do if I made some uh, make decisions from that? Okay, so the second order is much more subtle than the first one, and that's what we are going to explore here very quickly, but in a very basic analysis. So we have a physical inputs from the Solar Dynamic Observatory, like ultraviolet images. We have a time sequence of solar images from the I AI filters in the UV channel, and then we go to a kind of predictive model using, for example, LSTM and autoencoder. Okay, I'm pretty sure you saw those kind of models in the AI lectures. And from the encoder, we decode that. Then we understand the features, and we do some applications of LSTM in some pixels in here, and you can decode that. And from the decoder, we can get some kind of anomaly, some kind of extreme fluctuations here, as are the flares. And then we do prediction. We can do a statistical prediction if it's a Gaussian, non-Gaussian, okay, trying to understand a number of sunspots, okay, take into account PDFs and so on. And then we go to XAI. XAI, you can apply, for example, sharp and line that we are going to see in detail in a moment. And from that, we can say, we can confine that's the responsible to the extreme event that I got in the auroral jet is related to this kind of sunspots here in blue or in red. So if it's in red, the probability to that the extreme event in the Earth comes from this sunspot is very high. If it's blue, it means it's not a good contribution. Probability is very low. So that's a very high precision analysis that we are going to talk about. But the question is, what we learn in a first level? Okay, Which active regions, loops, or structures in the solar images driving the prediction? That's important, very important, because the sun is in rotation. Sun is very far from Earth, and in a real scale, if you take a ball, soccer ball, uh, as the sun, and you get a very, very small lead, like the same size of a grain of sand, you need to take like a 10 meters distance from this sand grain from the soccer ball to see the real scale distance between the sun and Earth. So it means that it is in rotation. Something happened in the sunspot, a kind of a coronal mass ejection, for example, responsible coming from that flare. So it goes like that to being around the Earth. So there are many models for that. I'm not going to show you here because you don't have too much time for that. But believe me, that the probability is not too high. You know, that's why it's very important to use some kind of XAI to see and to say which sunspots are responsible to the activity that we got in our planet. So we can do some physical interpretability of the model output based on the solar maximum. Second order. Second order XAI is trying to explain the process. Which modeling choices contributed most to the model performance? Okay, so we go from experimental design, like we have to training XAI or LSTM, for example. We needed to see explicitly the to run the model. I mean, we need to have the learning rate, the batch size, number of epochs of a trainment, holdout rate, how many data I'm going to test and to validate the model. Usually we take 70% to do the trainment and 30% to validation. We are going to use the optimizers functions as Adam, RMS probe. I hope you are familiar with that from the AI basics course. We have the dropout rate. That's a very important one to give a balance among the data we are using in the learning rate. And we have also the architecture, how many hidden layers we are using in our model, how many neural network units, and so on, from input and output. If it's an image in the output, you have many units. If it's just a time series, we have a few units. And we have also a kind of a high performance optimization framework. We are doing that by empirical choice, or we are using like a big frameworks as Optuna, Keras Tuner. That's a very important issue when you are opening the black box of the AI model. And also which kind of framework to do the calculations we are using, like TensorFlow, PyTorch, and etc. So from the experimental design, based on the specifications in the hyperparameter space, we go to many training runs. Okay, we design the experiments and do all the runs with for all those attributes from the model that I listed here. So we have the metric, like a metric for performance. It could be the mean square error. It could be skill score. There are many things that you can define here as the metric to this kind of a performance. Then we go for a meta model where we can plot the performance against the design space in high dimensions. We have many dates. We see which is the best GX function for evaluating this performance. And then we go to Shapley algorithm to understand which hyperparameter are more effective in this kind of prediction. So that's a very important issue concerning opening the AI black box. And then the second level, what we learn, which hyperparameters and design decisions most affected model performance, and also a guidance for efficient training, robust models, and better generalization. So to be in short, we have a level A, physical interpretation, that explain the prediction in terms of the physical world, focus on solar structures, regions, and their impact on the forecast. Then we have a level B, model interpretation, explain why the model is good or bad, focus on training strategy, hyperparameters, and design choices. And in between, we have a complete explainable machine learning life cycle. Okay, of course, we are going to improve the model every time. Some models, they are able to have data simulation and so on. So that's we call a complete explainable machine learning life cycle. So we can talk about two complementary layers of XAI lead to more reliable, transparent, and scientifically trustworthy machine learning systems. So that's the broad view of XAI. Okay, so let's go step by step in a more simple and detailed analysis. We have input data, observations, measurement, sometimes only information from context, because we are able also to use documents, use reports, so we can apply LLM models here. And we go to AI model, which should be a gray box, not a black box in the XAI interpretation. So we not only get a result, we also understand why we got such result. So in the output prediction, a result is produced by the model. So it should be transparent, traceable, and interpretable as much as we can. So, but we need to do that concerning the result. We see the result and we ask to the model in order to have some numbers to make a performance analysis based on those features. Okay, transparency, traceability, interpretability. So why this result? That's the most important question. Okay, important features, contributions, reasons, how it works, model behavior, patterns learning, and can we trust it? Uncertainty, validation, robustness. Some images that I'm showing you was made by ChatGPT 4. Okay, so when it happens, I put this stamp here on the right. Okay, and of course, these kind of questions, this kind of approach, we call XAI, is very, very important, as I told you before, for critical applications. And why all the space stuff are very critical applications also? Because we are dealing with what we call complex systems. Which is a complex systems? Okay, complex systems involve nonlinear behavior, nonlinear models, okay, non-homogeneous dissipation, energy and matter dissipation, okay, and we have a meta-stable configuration. It's not a stable configuration. Usually it goes from a meta-stable configuration to an unstable configuration. Okay, and you have phase transitions also. Sometimes you have a very uh, uh, astonishing phase transitions involved in the physical process. And then, of course, we need to be able to understand in a single view all those properties of complex systems. The most the most familiar way to see that is from the power spectrum that we studied in our first model. Do you remember that? We for the people that were in the first module for time series, we got from the time series the power spectrum. Power spectrum from complex system is a very uh, let's say a very important signature from the underlying process. Okay, because depending on the physical process that is based on the energy dissipation in the y-axis here. The energy dissipation is a function of the wave number. Wave number is the inverse of the scaling spectra that we are seeing from the fluctuations in a time series or even in an image. So when you plot a wave number, it's the inverse of scales. We see this kind of power spectrum that we learned in the first module of this course. So there are many different power spectral index. If you have a fully developed turbulence, we get this Kolmogorov minus 530 inertial regime in the power spectrum. But you have many others, like a non-homogeneous multifractal cascade, non-homogeneous cascades from nonlinear chaotic behavior, for example. We have a weak turbulence from complex Ginsburg-Landau models, okay, and many others. So it shows that the scaling process involved in energy dissipation is a very complex one. Why? Because all of them has this kind of have this kind of properties. Okay, nonlinearity, non-homogeneous energy dissipation, metastable configurations, phase transitions, and unstable configurations. Two very important examples from physics and from space physics are disruption in plasmas, where we go to a metastable configuration, depends on the space and time, initial conditions, and also frequency domain. And from a stochastic process, SP here, stochastic process, we go to a stable configuration, CU, that's also be observed in a given space, and that's function of time, spatial temporal domain, and also in a given amount of frequencies. So we see on the left a movie, a real one, from inside of a tokamak. Tokamak is a nuclear reactor for fusion. That's the future of our civilization. We are trying to get energy from tokamaks, okay? This kind of machine here, tokamak fusion. So we have this plasma formation inside the tokamak. We can get, for example, plasma infusion just from hydrogen and deuterium, and that's a very important one because you can do that using water. Okay, 1 liter of water is able to give you as 10 megawatts of energy, and we are when we are able to generate a 100 megawatt energy for 1 hour, you'll be able to bring energy for a whole city of 1 million people. So that's the future of our energetic transition. But why we didn't get success yet with tokamaks? Because there is this kind of disruptions in plasma. Okay, that's not stable. It's a metastable system, and it goes very quickly to an unstable configuration. So you cannot keep the plasma for more than a couple of minutes. And what we need to do is to predict inside the disruption, and then we need to stabilize the magnet to control the magnetic field to stabilize the plasma for long terms, like around scales of hours. If you are able to do that, you'll be able to get this energy in a very, very important way in order to do the energetic transition in our civilization. Okay. And in the right, we have the same kind of disruptions in plasma in a very different magnetic configuration. It is a magnetic looping. Here we have the toroidal configuration, but both in both cases we have a plasma. Okay, and the sun we have this kind of sunspots where we have this magnetic field, and sometimes it gets very unstable due to the interconnection among all the heads of the loops. Okay, and this is going to be we can do the visualization of this kind of dynamics in soft X-ray envelopes and also ultraviolet channel, and it goes out of equilibrium. Okay, strong non-Markovian component here in terms of stochastic process. So the Solar Dynamic Observatory is able to do some images and movies, okay, from this real. There is no artificial intelligence here, people. This is real data from real observatories, from real measurements. Okay, I used to say that because nowadays people see beautiful things like that and things that's artificial images or artificial movies. That's real data, and we can do very good analysis uh, even without artificial intelligence. We are able to do very good analysis on those data. Okay, some questions here. I can stop for a couple of seconds if anyone has a comment or a question.
So, what kind of data we take for this kind of analysis?
Excuse me, I didn't get the question.
So, here we are seeing the image data. So, we take the cutout from the image, or we take directly the images of the sun and then do this analysis.
That's a good point. That's a good point. We need to do both. Okay, that's a very important when you can get some analysis from the global solar image and also from the local ones. So we need to do able to do both things, because that's a very important point, because when I show you the X-ray Gauss time series, there is no spatial resolution. I know there is some kind of X-ray flare, but from the time series, I'm not able to say from where, which location it's coming as such a big flare, energetic flare. So that's a very good question. Yeah, we need to be able to do analysis both in the global scale and also in the local one. Okay.
Thank you, sir.
Y- Yeah, hello. Can I ask a question?
Yes, please.
Yeah. So you talked about tokamak fusion. So I'm very much interested in tokamaks. Um, is it possible to use this analysis to be able to solve instabilities in tokamaks or accelerators? Is it possible?
Yes, yes. Okay, that's a very important question because you have a many new. It's a very brand new research. Maybe just a few papers about that. I'm going to show you one paper. But we are very open in INPE in Brazil. I think BRICS countries should be able to make a bring new younger researchers and also seniors, of course, to work on those stuff, because people in tokamaks, we have for example ITER tokamak in Provence in France. I was there visiting the the biggest tokamak in the world, they still are assembling all the magnetic stuff. So it's time now, right now, to discuss how we are going to do some kind of internal analysis of these disruptions that we see here, okay, in order to predict it and stabilizes the field. That's a very, very new innovation brand in R&D. Okay, so at INPE, we have a new group just to study this kind of applications from artificial intelligence in tokamaks. So please keep in touch with us. Molevo can bring us together. Okay, maybe we can organize a course just about tokamaks and plasma physics in tokamaks for the end of this year or maybe next year. That because that's a very, very important issue for the BRICS country, you know, because the USA, for example, has many small tokamaks, and they are trying right now to stabilize this and to avoid the disruptions. That's the main goal in those projects. And in China, there is also the Sun, they call Sun. Sun is one very big tokamak as the one we have in France, and this is also need this kind of approach. So in Brazil, we have small tokamaks, but we are now moving all the tokamaks for just one center. And the people are doing that right now, you know. That's the state of art in R&D and innovation. And there are very big challenges that we need to face in the next, let's say, 10 years. So I recommend that let's keep in touch, people that are interested like you in tokamaks research, because we need people. We need human resources to this kind of studies, investigations, and ideas. You know, that's an open scientific market right now.
All
Okay.
right. Thank you, sir. So does it mean I can have your email? So I'll reach
Yeah,
out to you.
sure. I will give you. Okay.
All
What's
right.
your name? What's your name?
Harrison.
Okay, Harrison. Thank you.
Yes, sir.
Okay, let's move
Thank
on.
you, sir.
So let's take a look in this tool. This tool, the name is Anomaly Explorer with Deep Learning, IEDP. Okay, and this is a very, very simple application in the snapshots from the SCDO in this frequency 171 angstrom channel. This is from NOAA. Was observed many years ago, but it's a very good data, very high quality data, and because you have 180 good frames, snapshots for this time window, okay? And so it takes 20 seconds. It goes from this universal time. Okay, we have 20 seconds. 20 seconds is a very good time window to do some kind of prediction. So we have some snapshots from these 108 frames just to show you some of them. And the idea is to train this anomaly explorer with deep learning in order to predict the biggest dissipation that happens here. Of course, as you know, we have a few datas because most of them has a kind of a saturation at the end, you know, some kind of saturations. So when there is a bad quality like that, we need to avoid the data. But this one, there is no big saturation. So it's a real emission from the sun. So we are able to use this kind of data. So the idea here is to try to see in time where the maximum are in this image. So it goes from this place to this place, from place A to place B, place C, and place D, where we have the four maximum peaks in the time series. We see the first one here, the second one here, and C and D. Okay, so this is normalized values, and also in the anomaly explorer with deep learning, you use probability. Why? Because you are training. I'm going to show you the model. We are training machine learn with transfer learning methods to anticipate the probability of to get this kind of event. So we see the probability in yellow and green. The yellow one is a not good one because the delay is a very big one. It doesn't work to very well. So when you have a small delay, we can get here 41% for this D. It's not a very big probability, okay, but it's an interesting one to try to make some decision if you need, okay. So the question is, as we have AI here, why is important to take care about the interpretability? Because we can do some critical make decisions based on this kind of prediction, you know. So we need XAI also in this kind of tool. So traditional AI, we use the black box paradigm. Doesn't matter what happens here. Okay, I'm going to, from the input data, we go to output prediction, and what we don't know, why this result, what influenced it, how reliable is it, can we trust it, what is something changed, as I told you before. And we can get all the risks. Decisions may be taken without understanding, leading to errors, bias, or even harm. So the XAI approach should be AI model plus. What is this plus? Because it's not only a model, you know, it's a total, it's a whole approach that we need to take care here. We need to go beyond the model. That's the advice. So we obtain a prediction and understand why, how, and for what purpose. Okay, so we have open this. We can see who approaches, experts, developers, institutions, how it is approached. We use the data pipelines with such quality, methods, validation, assumptions, tools. Okay, and for what purpose? Scientific discovery only, monitoring, decision support, operational use, and with what responsibility we need to bring it to our approach, model plus something. Also the responsibility, because we can have in some terms auditability. So we need to bring ethics, governance, transparency, and regulation here. So from that, we have a foundations of trust: data quality, validation testing, documentation, transparency, and governance. So forget about to see this black box from now on. From now on, you are asked all those questions when we are working based on AI applications. So if you do that, you are doing XAI approach. And then we go to a result with trying to decrease as much as we can the uncertainty. So we go to explanations, why these results, future contributions, sharp and lime applications that you see in a moment, attention, causal insights, how does it work, model behavior, patterns learning, important variables, is it reliable, uncertainty, robustness, validation, sensitivity, what if, scenarios, counterfactuals, impact of change, many things, okay? And accountability, who is responsible? Developers, operators, reviewers, institutions, for the consequence, operational impact, user decisions, society issues like social effects, better decisions is need, okay? To understand it, trust, and responsibility. So I used to say that if you are a young guy now coming to the science application, research, and so on, started to learn XAI. because that's the future of AI applications. That's my advice, you know. So we have AI model plus, it means model plus approach plus purpose and plus responsibility. XAI turns predictions into understandable, trustworthy, and actionable scientific knowledge. So perspective, a broad perspective being as input data, AI model, machine learning or deep learning, it doesn't matter. And we go to this output that can be for prediction, classification, forecasting, and so on. Okay, so we have the first explain in this journey from input to output. Is start from explanation, what we are going to see in this course. Okay, and it's the focus here is to understand the internal reasoning of the model, feature importance, SHAP, LIME, attention maps, contribution analysis, local explanations. Then you can see a graph like that. Okay, in this afternoon, you see SHAP applications in astronomical data. Okay, in the afternoon session with Mariana Rubet. Example here is from space weather. Of course, the storm alert was issued mainly because intermagnetic field was strongly southward and solar wind velocity increased. So we can see some reports like that from the explanation analysis. Then we go to interpretation box. What does this result mean scientifically? Okay, focus give the result a physical and domain context. Physical meaning scientific consistency, causal relationships, domain knowledge, and contextualization. So, example, the model predicts a severe geomagnetic storm consistent with the arrival of a coronal mass ejection observed 48 hours early. Okay, this is very important, let's say, script from interpretation, let's say, step. And then sometimes we need to go to auditability. How was the model built and why did it fail or succeed? Okay, focus. Ensure transparency and traceability of the entire pipeline, since from the raw data to the deployment. Okay, we need to understand as much as we can the pre-processing, training, validation, testing. Okay, so we have data provenance, pre-processing steps, train, validation, test, split, cross-validation strategy, hyperparameter search using empirical criteria or Optuna like optimization frameworks, model architecture, versioning, and reproducibility. Example, the poor performance was caused by an inadequate train test split and the insufficient representation of extreme events. So, poor data, low data quality, not a good hyperparameter shoes, and so on. And then sometimes we need to go to accountability. Who is responsible for the consequences of this prediction? Focus. Define a responsibility and consider the impact of decisions. Operational impact, decision support, risk assessment, governance, human oversight, and responsibility chain. Example of a script output. A false negative prediction prevented operators from protecting satellite systems, for example. Okay?
Hello, sir.
Yes, please.
Yeah, I want to ask a question about the accountability that you talked about. What if
Excuse me. There are some noise. There are some noise or echo, so I cannot understand what you are saying. Okay, now it seems okay. Please go ahead. Hello, Mulebo, are you managing?
I think he's muted because his background is noisy. You can proceed. Yes.
Okay, let's go. So, trustworthy AI means interpretability, we understand why, plus scientific understanding, we know what it means, plus auditability, we know how it was built, plus accountability, we know who is responsible, plus reproducibility, we can reproduce and verify the results. So a prediction becomes trustworthy only when we understand why it was produced, what it means, how it was generated, and who is responsible for its consequences. Okay, so I guess it's very clear the complexity of this XAI approach.
Hello, sir.
Yeah, please.
Yeah. So about the accountability, is it possible for the XAI to hold itself accountable if it gives a wrong output?
Yeah, that's a very, very good point. Thank you for your question. Yeah, it's still we are here. We are in this right now. We have many, many tools for explanation, just a few for interpretation, not serious ones for auditability. Okay, and I think nothing for accountability in the pipeline. So that's a open, totally open research application. So people that are thinking about new thesis teams for research can explore new tools, new ways to bring interpretation, auditability, and accountability to the pipeline of XAI. People that goes to XAI meetings now are just discussing this kind of approach, explanations, sometimes interpretation. I'm going to the World Conference next month, July, next week, actually. I'm going to show you the World Conference on XAI to present two box for space weather prediction at INPE. Okay, I'm going to show things here, but I don't have anything to show here. Still, we are working on, but we don't have any published work on this kind of. There are something in new books discussing that, but it's a totally open research line. Okay, so please go inside of this because that's a very important, and this is in real development right now. Okay.
All right, sir. Thank you, sir.
Okay, let's move on. Okay, let's take a look now in the mathematics of sharp and line. What means sharp? Sharp means sharply additive explanations. Okay, it comes from the game theory. Game theory, we can talk about two kinds of games strategies. The first strategy is competition. The second one is cooperation. Okay, we have many games strategies that goes to only competition. The other ones that goes to cooperation, and there are some ones that goes. Of course, cooperation means also competition. If it's a game, there is competition. It's implicit competition. Okay, but I can have a competition with some kind of cooperation. When you have a cooperation, we have some techniques and methods, concepts, and one of them is the Shapley additive explanation. Why this name is Shapley? Shapley comes from a very important economist, Lloyd Shapley. It was a mathematician also. He got the Nobel Prize in economics in 2012. He died in 2016, 10 years ago, and he was the responsible to this strategy for cooperative games. Okay, and I'm sorry, this is in Portuguese. Okay, it's time to learn a little bit Portuguese here. I'm sorry for that, but I will translate for you. So the idea here is from behind the mathematics. Just to explain you with a very simple example. If you have a game, cooperative one, and you have a result for that game. Let's say it's amount of money or amount of points for 10 players. We have 10 people involved. Each people started with some amount of points or some amount of money, let's say $100 for each one, and there is a game. Doesn't matter which kind of game. But at the final, one of the players got, let's say, $500. So he got the most five times more than in the beginning. So if you are going to predict it, why that guy, one player got 500? If it's a cooperative game, someone in the game was trying to help that player. Okay, maybe they are in a cooperative way inside a competitive game. It works very well for many applications, even in teams, soccer teams, for example, and so on. And if I want to predict it, I need to be able to have what we call uh, 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 a first entrance value, and usually this phi zero here, okay, could be the average, for example, could be the initial value. Doesn't matter. It's a reference value that I have here. And we have the fx, okay, that is the result. So the result depends on initial value. When you use this phi here, it means the Shep value. You have initial value, and you have many model values here. Depends on what means those amounts. It should be, for example, anything I want. This is a very general model. Okay, it could be, for example, attributes, different time series values. It could be different values from an image. It could be different values for, in our model here, for those guys, for example. I can have some value for learner rate, batch size, number of applicants, holdout rate, optimizers. Although each one of that is a phi y in the Shep model, for example. Okay. So I have many entrance variables, x1, and it goes to the model f, and it goes for a prediction y. That's a function of f of x. The Shapley value, phi y, goes to this summation. Okay, that's the core of the model, because you have this a set of attributes n. Okay, S is the coalition of attributes. Each time each step you are going to the game pipeline, we start and we do some coalization. This coalization means some kind of interchange values, interchange attributes in this coalization. And then and of course, it goes in a very high amount, because it's factorial. We have many possibilities, okay, and there is direct related to the number n. So if you have 10 attributes, okay, we have a factorial of that. It's a very big number, okay, very number of possibilities. And then we have the subsets of that, doing the union set between all the equalizations and all the numbers of possibilities for each attribute. And of course, this is a difference between the reference and the subsets from the equalization. And it goes each time, the same time that we have attributes. So there is some rules. The rules means if we have 10 players, we need to set up our model in the simplest way with 10 equalizations, for example, like a position. If you have 10 positions in a room, each player is going to take one position. So the game is very, very simple. If one position is better than the other one, who is going to the better position in the room? That's the question. And that's what this Shapley value is trying to express in giving just one variable here. So we do the decomposition of a prediction. We are writing fx as phi 0 plus the sum of all the phi's, all the attributes, okay? And phi 0, as I told you, could be an expectation value, like average, mean, or even any statistical moment here. Depends on the application. And there is some axioms from Shapley properties. This number is related to the efficiency. Okay, there is some symmetry also properties, like if it's phi y equals to phi j, so it's they are interchange attributes, so it means symmetry. You have also the dummy component, because we are comparing the subsets with the whole set, okay, and that's very important. When they are the same, it goes to 0. And we have additivity from this formula, okay. It could be multiplicative, it could be convolutional, you can have a more complex Shapley models, but we are going to show you only the simplest way. Interpretation: if phi y is greater than 0, it's positive 1, it increases the prevision. If it's negative, it diminishes the prevision, decreasing the prevision. Okay, it's and it's the modules is a measure of the importance of this kind of descriptor or attribute to the final result. So to apply SHAP, we need to have the result. We need to have the inputs and we need to have the output. That's it. That's why it is, let's say, a XAI tool, because we need to get, it's applying based on results, based on predictions, okay? And on the right, you have LIME, local interpretable model agnostic explanations, okay? The idea here is to have the fx0 prediction by approximation, okay? Approximation of this initial function to the f for a simple model G in a neighborhood of x0. So if I have an x0, I have this neighborhood. If I call n x0 here, we have an instance to be applied, x0. So it's a local model gx. It should be simple and interpretable, okay? Like, let's say, activation function, something like that. And we have this model f, and you have the fx for predictions. Then we are going to compare gx0 with fx0 for local explanations. So LIME is a problem, is an optimization problem, because you need to minimize a g that pertains to j in a kind of composition, okay, with taking into account the balance between all the parameters. We are doing the summation. It's a very same approach of this one, okay. You have a summation here, additive one, okay, and we are taking into account the neighborhood approximation function. This is totally agnostic kernel. That's why we use agnostic explanation here. We can use them different functions here, and here we can bring some AI optimization techniques like what we use in. I'm not sure that you are familiar, but it's a very famous one. It's a k-mean, okay, k-mean uh, approach, optimizations for a distance of optimal point. We have also a kind of penalization here. We have this omega g. It's a penalty when this point is very far from this one. When it's very close, there is no penalty, or penalty is very low. So this is the penalty function that we need to bring to the agnostic model. So we have also GG is the set of interpretable models. You can use a decision tree, regression, linear regression. So that's a very, very open model to apply. Usually we can use a regression, linear regression for DX, okay, where we need starting from a beta zero a balanced value. For example, if I have too much different values in a given fluctuation domains for amplitude, we need to set up that and do, for example, the mean or just the summation to see like a very high area here represented as we call hyperpixel. Instead to have one pixel, we have the hyperpixel around this point. That should be an area in an image. For example, we have just a small area that we call pixel. We have many other areas, small areas around. So we have a hyperpixel here. It gives by linear regression, or even we can get a decision tree, okay, but not a so long one, okay, just a short decision time series with just one or maximum of two branches. Interpretation goes to this coefficients beta that goes to the, or if in this case we have rules tree for the tree. This indicates what attributes, which attributes are more important for prediction of this local value. Okay, so we have a local value. Which ones are more important? It's a Gaussian one. All those that are very important, and we have some regions that are more important than the others. That's what Lime brings to us, and those. So that's a very useful for images. Okay, this is a very useful for general applications, and is more specific for images. So examples here. For shop applications, we see this kind of output. Let's say we have some properties from our models, okay? Here, I'm not going to detail here, but I'm going to show you in a couple of minutes. And here we have the shape value. So it means that in red, the influence of such attributes are very positive to that prediction. And in blue, the influence of such attributes here is not so important to the prediction. For live applications in an image, for example, the solar image that we got from the example, there are some, for the maximum here, we see that the most important regions are that 2, 5, and so on. So it means the concept of a hyperpixel here. If you ask me, Professor, okay, that's important to do that, but we can also apply the same, can we also apply the same technique to, for example, to say if such image was produced by artificial intelligence for a generative AI? Yes, we can. We can use Lime or GradCAN, for example, that's based on the hyperpixel. Because when you ask for generative AI to create an image, believe me, there will be not pixel in that image. There will be hyperpixels, okay? Because it's a second order image. So we can identify a generative image applying this Lime or GradCAN, for example, GradCam is more powerful than Lime to get fake images. Why? Because he has a heating map. This is not a heating map. It's like a heating map, okay? But in using GradCam, you have a heating map. So there will be colors, okay, heating map, and you say, oh, that's a very hot place. It means that totally fake, made by generative AI. So you can use it also. And sometimes, for, someone asked me here about auditability, about responsibility. We can go for applying line or GradCam to images to find out if it was a fake one or not. Okay, that's a very important application. We are not going to face this here. We, as I told you, we will stay just in the first order XAI application. But for higher orders like auditability, we can use Lime or GradCam in order to say it was a fake image, fake in the sense that it was constructed using a generative AI. That's a very good. That's a very important in this kind of a discussion. We are not exploring this that, but you'd like to stress this here. Okay, for Embrace, we have, as I told you, I have two models. Model one goes from the time series from Gauss. It goes to magnetic, geomagnetic time series from Teenage, and it goes to ionosphere, electro auroral jet. And if you want to do a step back, one step back, we go to images from Solar Dynamical Observatory. That we call model one. Okay. Sometimes we call that model one and that model two. Doesn't matter here. But in the XAI layer, we have this kind of model. The auroral electron content, auroral jet, that's a time series like that, auroral index, is equals to a function of the Gauss time series that has this kind of delay, okay? And there is also a function of sin h that has this kind of delay. All those time series has the same time resolution. They are taking each minute in time, okay? And what we are trying to do here is to get 6 days of Gauss, okay? Get 6 hours of prediction in advance. Okay, that's a very, very good set to training AI. 6 days of Gauss to get 6 hours in advance of this one. Okay, why? Because there are between this and that like 1 day of delay, and between this one and this one there is around 1 hour of delay. So we can try to predict that from 6 days monitoring this data in a couple of hours this one. Okay, so if you are able to take this model in a good shape, we can do some temporal relationship and propagation delays from the sun to the ionosphere. Auroral means ionosphere. So model interpretation, AI index at time t is influenced by Gauss X-ray flux observed in tau 1 early and by the CNH index observed in tau 2 earlier. Okay, so pipeline of this application is like that. It goes from Gauss flux to the CNH, 1 day delay, 1 hour delay, and 1 hour delay. We are using Optuna to do the tuning of hyperparameters. This is a kind of XA interpretation. We are splitting how we tuned the hyperparameters. Okay, we are using LSTM forecast model. Okay, it's so we do explainability, open the box of LSTM using SHAP to see which kind of hyperparameters in the LSTM are more important to the prediction. So at the final, we have a 3D regression surface where we have a 3D representation of the three variables for a given one here value from this and for that. We can get one value for that in a surface from regression analysis. Okay, so we have a 1 day delay, lag-oriented architecture with some explanation, XAI explanation in the pipeline. So we have a GOIS in H. All of them goes to a LSTM memory of long-term memory model. In this architecture, we have the all the details of this that I'm assuming that we know a little bit about recurrent neural networks, and we go to these predicted values. So the model learns temporal dependencies from historical observations and predicts future system behavior. So SHAP here, we go to the SHAP applications here. Okay, I'm sorry, this is in Portuguese. I'm going to translate. Where phi0 is the base value from the SHAP model. Okay, this is the base value here is the one value for the auroral right now. Let's say I have this auroral value at the beginning, and I want to put this in the model to predict the auroral value at the final. And this is the value SHAP for all the three variables. So SHAP, FX using SHAP is like that in our model. We have the phi0, that's our rural value. You have the GOIS value, the SIMH value, and we have the SHAP output saying which one of them are more important to a given value, output value of X of our rural electrojet. So we see from here that SIMH in the first order application is the most important one. This is a very simple application. This is more to validate the SHAP than to use the SHAP. That's more to validate. Of course, you are waiting that SIMH, that is more closer to that, will be more responsible to the value that you get here. If you put SIMH at the beginning here, probably GOIS is going to be the more important one in order to influence the value of SIMH and so on. So applications for that, we have here just some examples from our models. Okay, we localize which kind of values we can start if I'm using images, for example, and we can go to the time series related to this SCDO for the model 1. This is for, so we are mixing in IA-deep model 1 and model 2. Okay, so from model 1, okay, we have these SHAP outputs. We have two outputs from SHAP, temporal contribution. So we have all the features of our statistical model. Okay, because you have a statistical model here in green. It's a non-Gaussian PDF that I'm going to show how it works in a minute. And we have this output saying that which kind of properties of the PDF in green are more important to influence the output. From the point of view of Lime, we have identified hyperpixels that we know those regions are more important, okay, to the peak that you are observing, and probably this is related with the GOIS X-ray flux giving us such kind of X class flare. So what we did here, we are opening the box, but you can also use this, bringing this information, especially information from Lime, to do some simulations, okay, from model. We can use, for example, hyperpixel values and go and bring that as initial conditions for a multiplicative cascade model, because you have a multiplicative cascade physics behind this behavior. So it means that explainable AI are helping us to do a kind of pin approach, physics inspired neural network applications. Okay. Why? Because someone asked me about how is going disruption research in both applications, especially tokamaks. But I have here some papers in the solar. Okay, two papers I recommend to you: evidence for small scale torsional alpha vane waves in the solar corona, the whole of no axis symmetry of magnetic flux hope in constrained solar eruptions. And we have also some papers for tokamaks, like this one, on the origin of plasma current spike during a tokamak disruption and its relation with magnetic stochasticity. So it is a real image from inside a tokamak in Czech Republic. The name is Compass Tokamak. Okay, so we have empirical model for multiplicative cascading plasma dynamics. Even in tokamak and solar plasma, we have the alpha vane number. This is related to the spectra that I told you, but not spectra in terms of wave number, but in terms of the phase fluctuations when you try to align the wave number and the magnetic field. So, so that's a very important models. Okay, because we have a turbulence and we have a kind of a shear physics behind that. That's strong turbulence, very fast models here, and the slow models here. It's important not for that, but it's important because from that I can get a time series from omega and q relate to the alpha velocity, and do some simulations in time, because time is implicit in this wave number. So I can get some time series like that, okay? And where we have this extreme. It goes like a cascade, multiplicative cascade. We can have models like Manevui Shriznavazan, that's published many years ago, but is related to a non-homogeneous cascade. Instead to have the energy here distributed in 50% here and 50% here, we just put 70%, for example, here, 30% here, and it's a non-homogeneous cascade. It could be used also not only for energy, but for matter and also for information. If I have a multiplicative cascade here, I can tell something to you, and for another people, and another people say something to other one, and you go to information multiplicative cascade at the end. So there are many fluctuations of information, matter, energy, and you have this kind of a time series. It has been observed in the multiplicative cascade, even in spatial temporal measurements in the solar corona, like waves here. And it means that we can create some 2D models for plasmas disruptions based on multiplicative cascade. And how XAI is helping us to give us some kind of initial conditions. So if you apply a deep expert anomaly for multiplicative cascades, we can simulate multiplicative cascades here. In the output for a deep, you have these normalized values and also probability. You normalize the amplitudes of some variable here. For example, the maximum in an image, or the average of maximum for a hyperpixel from line, and then we joint to this the probability. So we can do some prediction here from this peak. The first step is to detect the anomalies, and then we go to normalized value of P model and shifted predictions to get this simulation. It is make based on the concept of disruptions. So disruptions could be extremes, transients, or limey anomalies like that. We have 9 hyperpixels that it then can be used to identify in 2D some peaks and which one are more important. This guy is more responsible to that one. By approximation or even by weights in the nonlinear connection among many ones. So the metrics here will be like which metrics could be important here? The maximum or an average, take into account a hyperpixel instead of a pixel. So the physics model is based on multifractal analysis. Okay, this is not an easy issue to explain here because you need the statistical physics based on multifractal models. But I'm trying to bring to you just a glimpse of this algorithm. Actually, we have this partition function. Who is from statistical physics know what I'm saying. Partition function means I'm doing the partition of energy in a multiplicative cascade like that. Okay, like this one. And I can do that in 1 or 2 dimensions, take into account a sum of scale given by a probability based on, for example, hyperpixels. So I have I and j as a function of a scaling distance among them. And it goes as a power law, okay? That's the free variable here. And this power law goes also with a power law for the whole model that's related, for example, to inverse cascade. Could be in space or time or spatial temporal domain. When I do the z inverse of zx, I can get amplitude as a function of x, y, and t. Okay, and I can relate it also to that some discrete variables like the number of snapshots, probability, and also a tuning value to change, to adapt it, or to transfer learning, or for to choose a special kind of PDF, probability distribution function. So the Q here, I can use any approach for this power law. We are using a multifractal power law, where if you have this kind of fractal dimension and multifractal spectrum and so on. Okay, so from that I can define my probability in terms of a generalized extreme value model. It's not a Gaussian, it's totally far from Gaussian approach, so there will be no Gaussian here. And from that I can manipulate Q and R to get the best PDF from a generalized extreme value model. This is the model. I have 3 phi parameters here: localization, scaling, and shape. And I can change those values to get the best Pareto-like generalized extreme value distribution. Even Gaussian can be get from here. Okay, but that's what I'm using in the model. For example, for this one, this green line comes from a Weibull PDF. The best one was the Weibull PDF. I have a Frechet, I have many non-Gaussian PDFs, even log normal or Poisson distribution can be chosen when I'm doing the training here. So there is a transfer learning and also a reinforcement learning. What's the reinforcement learning? I'm doing penalizations here, as I do in Lime. For when the PDF is not a good one, I choose another one. So I'm doing this reinforcement learn during the life cycle of the trainment, and I'm transferring that to the model. So that's why for transfer learning, I can do this, the location of the green line. After many trainment epochs, I can be sure that the best PDF is the green one here. In that case, it's a Weibull, and I can anticipate this PDF for the training model to a real nowadays time series, okay, a new time series. It has been trained for many thousands of time series before. So from hyperpixel line, I can use a cascade model, okay, like that, a P model that it's this one in 2 dimensions using Y and J, and I can get the most extreme event regions to do this kind of predictions. Get the anomalies. Once I have the red lines here, I put that in the model. The model gives me the green line here, the green values here to predict the red ones. Okay, so the peak of green is the prediction for the peak of or each red peak. Red peaks means maximum peaks, maximum values around or average maximum values around the hyperpixel here. So I have this kind of model. That's a very interesting simulations, you know. So we have this 2D extremely multiplicative cascade that could be adaptation for solar plasma or even tokamaks, say, and then we have the extremes for from this kind of dynamics. So I have some maximums here, okay? That's totally non-Gaussian fluctuations. So I can apply all the techniques that we saw in the first module, do the statistical and spectral analysis of those time series, trying to understand the underlying physics. And I can also apply this AI deep tool with XAI to understand, to do the prediction, you know, as the results I showed before, like this, for example. Okay, so those are the maximum coming from those P model time series. Okay, to finish our course today, I'm going to show you where we are applying that. We have this Embrace in Brazil. This is the Space Weather Center in Brazil. We start from the sun, SCDO, Solar Dynamic Observatory. We go to GOES here, and we have a CNH, and somewhere here, actually we have DST, not a CNH still. And here we have the auroral index. And now we are going to put a 15 monitor based on XAI, LSTM regression and machine learning models to get this regression model. Regression model is, as I told you, in the model 1, we have the X-ray flux from the sun, the CNH from the geomagnetosphere magnetometers around the Earth, and here we have the auroral index. So for each value of GOES, I can get a value of AI for auroral AE for auroral jet. So it's a model for prediction and time, let's say. But it's a very good one. It still is not a very good one, but we have data simulation. The more we apply, the more it gets better. Okay, that's the idea of this regression model in this new output that's coming at the end of this year. So I'm going to present this demo from this application in this meeting in next week in Brazil, the Fourth World Conference on Explainable Artificial Intelligence. We had this demo approved, accepted to this conference, where we are going to talk about explainable AI for operational space weather forecasting, an interpretable prototype for the Embrace INPE monitoring network. Okay, so with this, I would like to bring you for more real important applications in real situation for space. With India and China, we are working on this diagnosing and predicting space plasma disruptions with embedded AI. We have this deep signal anomaly predictor that's based on the AI deep that I showed in the previously. And we are bringing XAI LSTM autoencoder for transfer learning here. We can bring this algorithm to this motherboard. Actually, there's a chip, the Hilo 80L. We can program this algorithm here we can go to embedded single board computers using a Raspberry Pi like this. This is that chip here in this motherboard, okay? And it goes inside a nano satellite. And we are trying to do predictions for plasma disruption in space. First of all, we need to validate this device. So we go to a plasma disruption chamber that we have in Brasilia University in Brazil. We are going there next month to starting to understand where we can assemble this, where we can put this kind of device in the chamber. If it's outside or inside, we still don't know exactly the technology. I'm not an expert on that, so the engineers are going to tell us which is the best way to do that in our application. This is a project that's inside of the BRICS initiatives. This is bringing China and India and Brazil. Maybe we can bring someone for South Africa also. It's a opening door for every contributions. Okay, so just let me know if there is someone interested and send me an email. Okay, so I'm going to finish here. This let me come back to the first transparency. Okay, please send me mail to reinaldo.rosa, okay, at imp.br. This is my mail, okay? And let's meet together in this afternoon, actually at the end of this afternoon, 1 p.m. here in Brazil, for XAI for astronomy and astrophysics, okay? That's the second model, and we have hands-on with Mariana. I don't have time now to show you hands-on for the space weather forecast, but I'm going to bring you the LSTM application. That's a very important one because I'm going to show you where are the bottlenecks, the problems related to applications of long short-term memory for time series prediction. We have some big problems because, any stochastic process, if it's a stochastic process, we cannot predict the stochastic process. Even if we have a coin, we want to predict the side of the pattern in a coin. You are not able to do that. Even a binary stochastic process with 0 and 1, we have 2 bits to choose. We cannot predict it. If I got 0, then I got 0 again, I got 1, I got 1, I got 0, 0, 0, 1, 1, 1, 0, 1. I know only that there is 50% to get 0, 50% to get 1. But how we can apply long short-term memory in order to predict a stochastic process? It's a crazy question. Do you understand me? So at the beginning of this afternoon session, I'm going to show how, when we can apply neural networks, recurrent neural networks as LSTM or other models, trying to predict stochastic process. Okay, so let's face this problem at the beginning of the next session. I'm not sure if it's the same students that will be there, but and then we go to astronomy, astrophysics applications. Okay, thank you very much. I'm open now for a couple of minutes if you have any comments or any questions. So Molebosh, now you are the manager. Please, you have
Sir,
the
can you hear me now?
yes.
This is Kiran from India. Thank you for the insightful presentation. I have a question regarding the shop. I already posted that point in the chat box. Can you check that one?
Sharp. Okay.
Uh,
This one, that one.
yes. Because in the base, the baseline prediction represented P0 in the model function. If P0 serves as the reference value, how do negative values arise? I mean, um, in what extent are they uh, how can you interpret those negative values? In what extent are they necessary in a 2 framework?
Yeah, that's a very good question. Actually, if we can improve the shape model, we can improve the shape model, bring some weights for the blue and the green. Okay, yeah, excuse me, the red and the blue. We can get some weights for that. Here, the weights are like a blind values, so I cannot explain them here. I just it's a quantitative one, not qualitative analysis. But I can bring some weights that I can transform in qualitative issues, like satisfaction, not totally satisfactory, and so on. Uh, uh, but it is still not in the model, It still is not in the model. That should be like a research issue, and I cannot give you an answer, a precise answer about that. It's
Thank you,
a
sir.
Okay. Thank you.
Thanks, Prof. Shubham?
Someone is asking.
Yes, Shubham has a hand up. Go ahead and speak,
You can also write some questions in the chat if I'm not. I'm not sure that there is this possibility, but you can write. If you don't want to ask, you can write something in the chat, and Molebo can.
Hello?
Perfect. We can hear you now. Yeah.
Okay. Yeah, so I have a question on the model prediction. So when you do predict using this extensible AI, right? So how good is the prediction? Like, do you define some kind of a probability distribution or like some confidence interval for the prediction, like
Yeah,
based on the values
yeah,
or something?
yeah. That's a very good question. No, at this time, this is only empirical one. We need to bring this quantification here for uncertainty. Okay, uncertainty here is just empirical analysis. Okay, we can say for the sun application. Okay, this one, for example. I just see here and say, okay, 41, what I'm going to do based on that one? I'm going to turn on something or turn off something. That's the only, but we need to bring offshore, of course, some quantities for the uncertainties and bring that for the make decision. Thanks for the question.
Oh, okay. Yeah, thank you.
Thanks. Any other question? I don't see any questions in the chat. If you do have any questions, maybe raise up your hand. Okay, perfect. I think we'll take silence as that there are no questions. But if you do have any questions, we still have the Discord channel. Please post your questions within the consultations or either the one of the channels there. I think someone will attend to your questions. Prof, thank you so much for this wonderful presentation, Prof. We highly appreciate your time as well as your expertise on this. And from us at Briggs as well as the students, we really appreciate your time taking it to present this presentation. And thank you so much. I think we'll meet in the second session later on today. So
Yes.
thank you.
Thank you very much, Molebo. I just want to say to finish my lecture that we are working on a booklet. It is still not already done, but in a couple of days we will have that. Maybe this afternoon I'm going to show you a draft, but it means that a post material that everybody can use it to study, to go deep in some details. So we are preparing. It's a very high quality material. There are two booklets, one booklet for a time series and the second one for XAI. Okay, so all of you we will receive that from Oleboj, this kind of material in a couple of days. Thank you, and see
Perfect. Thank you
you.
so much, Prof.
Thank you, Professor.
Okay, bye-bye. See you later.